Hi, my name is Masood. I'm a PhD student at the University of Illinois, Chicago. I'm going to talk about our work which evaluated a bunch of cross-platform apps. This is work I did with Mo, who's a friend, and he graduated last year and he's working at Palo Alto right now. And also my advisor, Chris, who's right there, and also Jason, who is vacationing in Greece. So here's me presenting a work which took around 18 months or so to do. And one of the first and most important things we learned from doing this work is web browsers are awesome. Web browsers, I love them because they essentially have been developed and continue to be developed by these large teams that actually care about your privacy and your security. And I don't mean that we live in a utopia. I basically mean that from working on Electron apps for 18 months, this looks a lot better. What's happening, unfortunately, is a bunch of developers want to provide you a bunch of native feeling APIs, and they want to retain users, which is us, understandably. Some of these features are hard to access when loaded within web browsers, so they want to offer apps that load within your desktops and are separate from browsers themselves. But when they do this, they use frameworks like Electron that make it very easy for them to take code that they already had to run on their websites within web browsers and put them directly into these apps. But while it looks simple and like fits in a simple, nice looking sentence, it's very complex and it's very error prone, as you'll see in the slides that I have after this. We essentially built a framework which we are calling Inspectron. We actually wanted to call it Auditron, but apparently it's Xerox has a patent on it. But Inspectron is an automated dynamic analysis framework. It basically lets you run these apps within an instrumented version of Electron and gives you a report on the various security and privacy misconfigurations, vulnerabilities that these apps may have. Using Inspectron, we essentially managed to send 106 bug reports. 2 of these were to the framework themselves. And also the apps that received this included some of these popular apps like Postman, which is like a developer RESTful API testing app, and WordPress, which is used to make websites and stuff. One of those was also a high severity CVE that luckily has been patched since. So to explain in very basic terms, and not to dumb it down too much, but essentially to give you an idea that things change fundamentally, I'll give you a comparison of what happens within web browsers and why it's different from Electron. So say you visit a site within a web browser. The blue thing is supposed to represent the site. It's just got generic content in it and offers you a bunch of services. This site can load external resources that may be like ads, that may be like other scripts from third-party content that essentially expands these services that they offer. When they load within a web browser, the browser takes care of how to divide these things, how to ensure that caches are different, how these things can communicate with each other, and more essentially, and what we'll deal with in this talk, is how it safeguards everything that runs within the web browser and what gets loaded from the rest of the user's device. Electron, essentially, what it does is it lets the developers just take what was already running in a web browser and renders the same thing using the same browser engine with a few patches, but what looks like exactly what you'd see in a website. But it also allows developers to configure a bunch of features directly into what it's called a privileged or main process, and has a bunch of other additional configurations that can run on the device themselves. When it does this, it essentially asks developers to make choices now and have answers to questions now that they did not need to have when they just loaded a website directly. So the big, bold red box that you had seen before now becomes dotted because it's up to the developer to configure how much of this isolation is required. Even within the processes, they determine what these 2 processes communicate, how does privilege get transferred between these 2 processes. Standards like same origin policy do not apply, and it's up to developers to actually decide whether they want to implement same origin policy. If you're within, say, a note-taking app and you click on a link, you do not want the link to be taken out by a complete Google page or a Facebook page when you're actually still inside the note-taking app. Handling that is up to the developer as well. And finally, if you say you sign in, you have some secrets, you have some sensitive files, you want these to be encrypted, that's again with the developer. There are a bunch of options essentially that they do not need to think about. So while it might sound straight and simple, it just becomes very complex and as a result tricky and as a result error prone. So when we wanted to evaluate apps using Inspectron, the rough high-level idea is we just download the packaged apps themselves after they've been obfuscated, minified. So even if we cannot read it, we still can access the files themselves. We look at the versions that they use for underlying libraries, the Electron, Node.js, Chrome versions. So we know what to instrument with, and I'll get to that, why that's important in a bit. Followed by, we just take the source code, plug it into our instrumented version of Electron. And once it's up running, we connect with it through a Puppeteer script and also perform a bunch of other tests and combine all of these sources to give you an extensive report of potential misconfigurations, things that can then be considered vulnerabilities and how these can be chained. A very important part of this is the instrumented version of Electron. And to give you an idea of why this is complicated, just the part that includes Electron's additional code that's added on to Chrome or V8 and other NPM packages is spread across different, not just directories, libraries, and scripts, but it's also partly coded in TypeScript, partly coded in C++, partly coded directly as shell scripts as well. And all of these just intermingle and interact. So say, as a very basic example, and this is just to give you one purview, you start an app, it calls a particular script that in turn passes your command line processes, command line switches that determine if you want to enable any experimental APIs, if you want to send something to V8, if you want to send something to Node, if you want to send something to Chrome, after which you just want to now open a new window. But that window has a different session. Does that window need to be given the advantage of actually opening another window? Should it execute JavaScript within it? That's decided by one script. Another one decides how much privilege that has. Another one decides how they communicate with the main process. And all of this roughly goes into creating a single window. And this entire process is repeated each time you add another frame, another web view. This opens another window. And the red little dash boxes are where we went ahead and instrumented stuff, but that's only part of the total instrumentation that we had to do. When we eventually went and downloaded a bunch of apps, this was in May 2023, we basically made sure that we had the latest version of that's available for a bunch of apps. Each of these apps, we extracted the versions for them, and we discovered that a lot of these apps do not have the latest version of Electron, and as a result, the latest version of Chrome. Some of them went back as much as 4 years, the oldest being one that depended on a version of Electron that was released in May 2019 when we were instrumenting them and analyzing them in May 2023. And why that's important is because Electron is built on a bunch of underlying libraries. It has patches to a particular version of Chrome. It has patches to a particular version of V8 and Node.js and things like that. So when it has patches for that, it repackages everything and is distributable, which again gets repackaged when apps build on top of Electron. So if anything was built on a specific version of Electron, we had to specifically test that app against that particular version of Electron. So we created a new instrumented version of Electron for each major framework release. And we had to do this 24 times to create different versions that worked on both macOS and Linux. I'll give you an idea of the kinds of problems or just the categories of problems that we found. One option that Electron offers is for app developers to now directly use Node.js APIs. So our old friend, the same diagram, I'll keep this consistent just so that it's a little easier to understand. Now, Electron allows you to have native features, which would be to like write to files, read from files, execute other apps on the system directly. And that's mostly privileged stuff, and that's supposed to be within the main process. And Electron actually recommends, as much as possible, just do all of these privileged things in the main process. And if you need anything to come down from the renderer to the main, decide these individually and expose them individually. But developers may not always think of this as an easy thing to do, especially if they have a lot more to expose, a lot more functionality to expose to the render API. So as a result, 49 of the 109 apps that we evaluated completely took out these safeguards, which basically meant that anything that's loaded now has direct access to the user's device and can just execute another app on the system and modify stuff on the system. And worse still, if you have third-party content that has these privileges, it can directly add, write, read, edit, access all of these files as well on the user's device. Note that this was not, this was completely prevented by web browsers as is. Similarly, when you talk about security on the web, one of the main critical fundamental ideas is same origin policy, which basically prevents interactions between content loaded across different origins. But Electron allows developers to relax this isolation and allows developers to enable such communication between different third-party origins. And as a result, these components can use malicious interactions to basically attack each other. We found at least 8 apps completely disabled this standard feature. And as a result, any third-party iframes loaded within them can not just interact with each other, but consider an example where you have specially created a sandbox isolation safeguard around specifically loaded third-party content frame. But if you've disabled same origin policy, they can directly bypass all of that and attack the user's system. As an overview of our overall evaluation, those 2 examples that I gave make up 12 of the web preferences that we check. And those 12 web preferences in turn make one class of misconfigurations that we check. That one class is a part of 16 classes of misconfigurations that are implemented within Inspectron. But once this has been built, it can be used over and over again to identify misconfigurations across a range of apps. As a result, we were able to just reuse this code and reuse our versions to automatically report on misconfigurations from over 109 apps. I'll give you an example of the type of vulnerabilities that we actually found and reported. One being a popular service, WordPress, which allows users to build their websites, also write their blog posts, manage their WordPress account, but also engage with comments on their blog posts and things like that. WordPress offers an Electron app, which essentially for the large part of it is just ported from their website directly. So although it looks like a native app and it lives in a different bubble on your system, it looks almost the same as it would within a web browser. So it has your home, it allows you to write your blog post, look at your comments, go through your account, things like that. But when we evaluated it using Inspectron, we noticed 2 important misconfigurations. One, that as of May 2023, the latest version used a really old version of Electron, and the version of Chrome that it depended on is at least 3 years old, which at that point had a bunch of public exploits available. The second one was that it did not have listeners to restrict navigation. So you could be on WordPress, and if you found a way to navigate the site away, there would be no restrictions and the window would be taken over. So we essentially created a simple example attack where, say, a victim's blog is available publicly. The attacker just goes to the victim's blog, reads the post, adds a comment, embeds a link. What the victim sees within their comments is this particular link that the attackers left, which if they click, navigates the site away completely. As a result, what was previously WordPress now is just the attacker's site, which is being executed on an old version of Chrome, which has a bunch of exploits that they can just use to create an RCE attack and take over the user's system. There are 3 things that I'd essentially boil this talk down to. One is that Electron's a good idea in that it provides a bunch of features, but it also creates this whole range of new vulnerabilities that need to be evaluated and basically confuse developers. We created a dynamic analysis system that just does just that. Thank you. It basically analyzes these apps and reports on the vulnerabilities we find from it. And we, as a result, sent 106 bug reports, including a high severity CVE, and also received a bunch of rewards for them. And these included apps that are quite popular that include WordPress and Postman. We made our artifact available, and I'd encourage you to use them. I'd encourage you to expand on this research that we have, and feel free to reach out to me with any questions you may have. Thank you.